All right, vectors part two. As I said, you now have to learn some addition, so I'm going to complete the job that the elementary school teachers began, and we're going to learn how to add vectors. Uh, let's start off just by thinking. Let's take this example right up here. Two people are applying a force on a box. One person is applying a small force here, another person a much larger force. Now, in which direction do you think this box is going to go um, intuitively? So I think since this force is so much bigger, it's primarily going to go to the right, but it's going to go a little bit up as well. So it's going to go off somewhere like that. Now this one down here, these two forces look pretty close to being equal. So it's probably going to go off somewhere in that direction right there. Right? Now, thinking about this intuitively is a great check once we know the method here, because there's a lot of ways to muck up the method, but if we always use our head and our common sense and think, where's this thing actually going to go, that's really, really helpful. All right, so now for the full-on method of how to add vectors when they are at weird angles. Step one is put the vectors what's called tip to tail. Now, vectors are arrows, so think about like a bow and arrow, like that's being shot. This is the tip of the vector. Ow! Ooh, ow! It's hurting the mouse. And this is the tail, where you would put a little tail feather if this were an actual arrow. So we're going to put these two tip tails. So I'm going to take this little vector and bring it up here and plunk its tail right here onto the tip of this vector. And I'll do that like this. Voila. So now they are tip to tail. Now our next step is to draw in the vector sum. Now these two forces, we've got a big force to the left and a small force upwards, so the vector should be going mostly to the left but a little bit upwards. So it should be like this. It should be a little arrow pointing in the up left direction. Now I'll start by just drawing in a line, because you can, if you just do this by yourself, you're pretty sure that there's a line connecting the here to here. And a lot of people get confused and make it go in the opposite direction, down and to the right. But if you are thinking critically, you know that's totally not what should happen. You're pushing this thing to the left and up. It should go left and up, not down and right. Another nice way to think about this is to think about the days before GPS. They were dark days indeed. And we old timers like myself, resorted to stopping and asking random people for directions. And this worked out about as well as you would think. So imagine I am lost and I stop and ask for directions, and somebody very confidently tells me the totally wrong way to go. So I follow their directions. My mouse keeps disappearing here. Let's cut that out. And I'm told to go this way. Now I reach this point and I think to myself, well, that was totally wrong. So I stop and ask for directions again and finally get somebody who knows what they're talking about, and they tell me to go a little bit due north, and then I'll arrive at my destination. When I finally get there, I think, I took this long circuitous route, but I could have, if I knew, I could have just gone the correct way like that. I could have simply gone up and to the left like this. All right. Now, finally, we want to actually add numbers. So let's make this a net force problem. One of these forces is 8 newtons, the other is 2 newtons, and we would like to figure out the net force or total force. Well, we know it's not 10 newtons because that would only be the case if they were pointing in the same direction, nor is it 6 newtons, which would be the case if they were pointing in opposite directions. If those two forces happen to be at a right angle, then this problem is fairly straightforward. This becomes a right triangle, and I believe that you've seen right triangles before in your math classes. So if your math teacher threw this right triangle at you and say, figure out with this length right here, I bet you could do it if you remembered to use the Pythagorean theorem. So you do a squared plus b squared equals c squared. You know your a and b, you can solve for c, and if you do this out, you'll get about 8.25 newtons. All right, so let's sum up. How to add two vectors. Step 1, put them tip to tail. Step 2, draw in the vector sum, just remember the direction is the trickiest part of this. Either remember the common sense intuitive, think about which way it's going to go, and or think about bad directions, where you get bad directions and then you say, I could have just taken the shortcut and gone straight there. And then finally on step 3, if those two vectors are at a right angle, and in this class they will almost always be at a right angle, then you can use the Pythagorean theorem to figure out the net force, or add the vectors if we're adding velocity vectors or something like that. Okay, so let's practice this. Here are two vectors. So my challenge for you is to figure out the net force, add these two vectors together, and tell me which direction the net force is pointing. Is it up and to the right? Is it down and to the right, down to the left, up and to the left? That's kind of what I'm looking for. All right, take a moment, pause the video, and I'll tell you the answer after you get back. Okay, let's do this. First, we put them tip to tail, kind of like this. So I move this 4 Newton vector kind of right over here. So now they are tip to tail. I draw in my vector sum, and since this vector is pushing down, this vector is pushing to the right, the vector sum better be going down and to the right, and so I know which direction it's pointing. And if I use the Pythagorean theorem, I get 5 newtons as a force. Or you could just remember that this is a 3, 4, 5 triangle. Okay, sample problem number 2. Find the magnitude and direction of the vector sum. Add the two forces together. Pause the video now and do it. Okay, so some of you might have taken these two vectors and said, ooh, look, they're already together. This Mr. Chipkin makes it so easy, and drew a line right here and put an arrow on one direction or the other. And if you did that, unfortunately, you are very, very wrong. I'm sorry. And the problem is, are these two vectors tip to tail? No, they are not. They are tail to tail. And that's not how we add vectors. So we have to move one of the vectors that are tip to tail. So I'll do that right up here. I move the 9 Newton vector. I don't know where the 9 Newton went here, but there's 9 Newton, so I just move this vector right over here. And I drew in my vector sum right here. I know from this diagram that it must be going down and to the left because this vector points to the left, this vector points down. And then if I use the Pythagorean theorem, I get exactly 41 newtons right here. Now I know, Mr. Chipkin, you're just trying to trick me. You're so mean by putting them tail to tail. That's terrible of you. Well, when we draw free body diagrams, we have like a little object somewhere, and then we draw vectors pointing away from that object. So this is actually usually how we draw forces. When we draw them free body diagram, they're all tail to tail. So this isn't that out there. And I'm still mean, but you knew that already. Okay, one final note about what to do if vectors are not at right angles. How do you find the vector sum then? This is quite rare in this class. It's pretty common in nature, but we're probably going to stick with right angles. But if you ever come across this kind of problem here, here's how you handle it. You follow steps 1 and 2. You put them tip to tail. You draw in the vector sum. So I've done that right over here. And then you can't use Pythagorean theorem because this is not a right angle. So there's two methods. One, you can use fancy schmancy math called trigonometry. And if you don't know that fancy schmancy math, you can get out a ruler and a protractor, and you can draw your 2 Newton force 2 inches long, your 3 Newton force 3 inches long at the correct angle that you've measured with your protractor. And then you plonk your ruler down and measure the vector sum. And however many inches that is, that's how many newtons you've got. So basically, just draw a 2-scale diagram and you've got your answer. Okay, so to sum up, we've learned about vector addition. We've learned why we care. And we have learned about how before you should approach any problem, you should think intuitively about which way the vector sum is going to point. We talked about the tip-to-tail method, and then we talked about how to do a 2-scale drawing if those vectors aren't at right angles. All right, good luck!